Next section of chemistry, guys, is about the organic chemistry, and these three lectures, lecture 22 to 24, are about the saturated hydrocarbons, about the alkanes and the cycloalkanes. I have divided these lectures in three parts because of the too much large size. Therefore, 22, 23, and 24 are all divided. So the basic objectives of these three lectures are the chemistry of carbons, alkanes, cycloalkanes, geometric isomers of cycloalkanes, and the reactions of these compounds, alkanes and cycloalkanes. First up is the chemistry of carbon, and some basic knowledge is that there are a lot of organic compounds in nature basically, and carbon is a part of all of these organic compounds. So the question arises, why are there so many organic compounds? And this belongs to the fact that carbon have some special properties which no other element has. And some of these properties have been mentioned here. So carbon can form stable covalent bonds with other carbon atoms, and the fact is that carbon can form up till four covalent bonds with other carbon atoms. So this point is important. Apart from other carbons, carbon can also form stable bonds with other elements like oxygen, nitrogen, sulfur, halogen, and when these elements are present, these will confer many new physical and chemical properties to that organic compound. Another property of carbon is that it can form double or triple bonds with other atoms to produce a variety of structures with different properties from each other. So as we can see in the diagram, it can make a double bond with carbon as well as with the oxygen, and it can also make a triple bond again with the carbon, with another carbon atom, and also with any other atom, which in this case is nitrogen. Another very important property of carbon, for the reason that it can make so many organic compounds, is that the number of ways by which we can arrange these carbon and other atoms in these different compounds, which is nearly limitless. Carbon, including structures, can be branch chain, they can be linear structures, or they can be ring structures or cyclic structures. So this one is a linear structure, like in a straight line, uh, which we can see here. And then we have the branch structure, in other words, which have got a branch in it, just like a tree. So this is the example of the branch structure. And then we can have the ring-like structure, which are also commonly known as the cyclic structure. So in this one, carbon is making a ring or a circle. Next up are some important differences between organic and inorganic compounds. And the first difference is the type of bond that is present between them. So organic molecules mostly have covalent bonds inside them, and on the other hand, the inorganics usually have ionic bonds. And we all know that covalent bonds are formed by electron sharing, whereas the ionic bonds are formed by the transfer of the electrons. Moving on to the second difference is the structure basically, and the organic molecules are mostly non-electrolytes, and they can exist as singular molecules, whereas the inorganics are usually three-dimensional crystalline structures, and they are often soluble in water, and they dissociate into ions. So therefore, they are known as the electrolytes. Another difference between the organics and inorganics is their melting and boiling points. So organics usually have lower melting and boiling points, whereas the melting and boiling points of inorganics are usually higher. And this is mainly due to the fact that the intermolecular forces in organics can be broken fairly easily. So the bonds can be broken fairly easily, whereas in the inorganics, there are ionic bonds, and they require more energy to break them. Therefore, their melting and boiling points will be higher. Next difference is water solubility. Organics are generally non-polar, so they are water insoluble because water is a polar compound. Whereas the inorganics are mostly water soluble, readily dissociate in water. Moving on to the classification of the organic compounds, and also known as the different families of organic compounds. And the most general classification divides these organic compounds into hydrocarbons and the substituted hydrocarbons. So these are the two main categories. The first big category is the hydrocarbon, and which by definition contains only carbons and hydrogen atoms in them. That's why the name hydrocarbon. They are non-polar molecules, and because they are non-polar, obviously they will be not soluble in water, as water is a polar compound, and they will be soluble in other non-polar molecules. Like a couple of examples are given: toluene and pentane both are the organic solvents, so they are non-polar solvents. These hydrocarbons are usually made or constructed of chains or rings of carbon atoms. So carbon atoms will be joined with each other, and there will be sufficient hydrogen atoms basically that will be joined with the carbon, so that the carbon can fulfill its four bonds, as one carbon atom has a tendency of making four bonds. So the hydrogens basically will be consuming up these bonds inside the hydrocarbons. The second family of organic compounds is the substituted hydrocarbons, and by definition, the substituted hydrocarbons are such compounds in which one or more hydrogen atoms are replaced by any other atom or a group of atom, and that will be known as the functional group of that compound, the substituted element or a group of atoms. So the first family of hydrocarbons is divided into two main categories. One is known as aliphatic, and the other one is called aromatic. So this is the subdivision, or you can say classification of the hydrocarbons. Now, aromatic are the compounds which are cyclic in structure basically, so they make ring-like structures as seen here. Aliphatic category is further divided into four main types, which are classified as alkanes, alkenes, alkynes, and cycloalkanes. So these are the four categories basically, with different general formulas, and these formulas are absolutely important to remember for alkanes, alkenes, alkynes, and cycloalkanes. So the first one, alkanes, are the compounds that contain only carbon-carbon and carbon-hydrogen single bonds. So the word or the key word to remember is single bonds. There are only single bonds present between these hydrocarbons, and as they are hydrocarbons, obviously they contain only hydrogens and the carbon atoms. And these compounds which only have single bonds in them are also called as, another name is there, which is saturated hydrocarbons. So saturated hydrocarbon is a hydrocarbon that has no double or triple bond. In simple words, it has only got no double and triple bonds, it has only got the single bonds in them. Alkenes and alkynes, on the other hand, are considered to be or called unsaturated hydrocarbons because they contain at least one carbon-to-carbon double or triple bond. So unsaturated hydrocarbons are the ones that have at least one, or they can have more than one double or triple bond, and that bond will be between carbon-carbon always. So in the diagram on the left side is shown a saturated hydrocarbon. As we can see, all the bonds between the carbon and other carbon are single bonds, whereas the unsaturated hydrocarbon is the one which have at least one double bond, and it's actually the double bond that is shown in this figure. Next are the cyclic structure of hydrocarbons. Now some hydrocarbons are cyclic because they form a closed ring or a ring-like structure basically. These are of two types. One are known as cycloalkanes and the other one is known as the aromatic hydrocarbons. And the only difference is that cycloalkanes have got saturated hydrocarbons in them, whereas the aromatic hydrocarbons are unsaturated hydrocarbons. In other words, they've got double bonds in them, and usually they have a benzene ring structure, which is shown in the diagram as well. The structure of benzene, which has got 6 carbons and 6 hydrogens, so C6H6 is the formula. On the left is shown a cycloalkane, and that one also has 6 carbons in it, but hydrogens are 12 in it. So C6H12 is the formula for this cyclohexane. So cycloalkanes saturated means only single bonds, whereas the aromatic hydrocarbons have double bonds in them, and both are ring-like or cyclic structures. So as a summary, these hydrocarbons can be divided into two main groups, basically saturated hydrocarbons, and this include the alkanes and cycloalkanes if they are cyclic in nature, and the other variety is the unsaturated hydrocarbons, which have got double or triple bonds in them, and these include alkenes, which have double bond, alkynes, which have triple bonds, or aromatic, which are ring structures having double or triple bonds in them. So a bit of detail about these alkanes. They have a general formula which is very important to remember: CnH2n plus 2, whereas N is the number of carbon atoms in that compound. The sources of these alkanes are usually petroleum and the natural gas, and they are saturated hydrocarbons. By definition, they will only have single bonds, and these bonds can be between carbon-carbon and carbon-hydrogen. Now the formulas used in organic chemistry are mainly of two types: molecular formula and the structural formula. And the molecular formula, sometimes also called as the chemical formula, mainly lists the kind and number of each atom basically. So it only tells us the number of each atom and what type it is basically. So C2H6 is a molecular formula, and it's telling us C or carbon is 2 atoms and hydrogen is 6 atoms. So that is the only information it gives us. Similarly, C6H8 or any other molecular formula. Structural formula, on the other hand, shows us each atom as well as each bond in the molecule. So it's giving us additional information about the bond, and we can see these structural formulas at the bottom basically of the same two compounds at the top, C2H6 and C3H8. Next up is the condensed formula and the line formula. So condensed formula basically shows all the atoms in a molecule in a sequential order, indicating which atoms are bonded to which atom. So the example shown here, CH3 bonded with the CH3, and the bond is a carbon-carbon bond basically, and another one CH3 CH2 CH3. So for condensed formula, basically the word to remember is the sequential order. Another type of formula is called the line formula, which assumes a carbon atom at any location where the line intersects. So it is simply assuming that a carbon atom is present at every intersect, and we also have to assume that each carbon is bonded to correct number of hydrogens, depending upon which type of bond it has. So the structure here, which is C3 bonded with CH3 bonded with CH3, can be simply represented by this line. So at one end of the line, we have assumed that a carbon is present on this side and also on this side. And we have also assumed that there are a correct number of hydrogen atoms bonded with each carbon. So because this bond is a single bond between the two carbons, and each carbon has to make 4 bonds basically, so there must be 3 hydrogens present here as well. And similarly on this side, one carbon is attached with the 3 hydrogens to complete its 4 bonds basically. So it will be the same thing like this one at the top in the condensed formula CH3CH3. Whereas the second formula CH3CH2CH3 can be simply represented by this line formula again, which is assuming that 3 carbons are present in this molecule, and each carbon is bonded with correct number of hydrogens. Next are the names of first 10 continuous chain alkanes, and we know the general formula for the alkanes is CnH2n plus 2, where n is the number of carbon atoms. So if carbon is 1, hydrogen will be 2, n which will be 1. So 2 multiplied with 1 gives us 2, plus 2 gives us 4. So it, in other words, it means that it will have 4 hydrogens and 1 carbon, which is the formula for methane, CH4. Ethane has a C2H6. Again, we can apply the same general formula, CnH2n plus 2. Then with the 3 carbons is propane, butane, pentane, and so on up till the C10H22, which is known as decane. An example is asked at the bottom: which of the following are alkanes? So C7H18, basically we simply have to multiply the number of carbons with 2. So 7 multiplied with 2 in this first example will be 14, plus 2 will be 16. So this one, or A, is not an alkane. C7H16 is an alkane, we just calculated. C8H16 again cannot be an alkane, because when H2n plus 2, 2n will be 16, plus 2 will give us hydrogen number 18. So C is also not an alkane, and the last example is an alkane as well, C27H56. Next is an example just to test the formulas that we have just discussed. So the question is, write the structural and condensed formulas for the following line formula. So line formula has been given for trimethylpentane, also known as isooctane, and we have to write the condensed formula and the structural formula. So in order to write the structural formula, first up we simply have to place the carbon skeleton wherever the intersect is present. There is 1 carbon here, 1 here, and each at the edge as well, as I am mentioning. So simply write the C or carbon here. That will be the first step in writing the structural formula. So we can convert this one into a shape like this. Next up is simply we have to add the correct number of hydrogen atoms to each carbon. So this carbon, because it's only making a single bond with this second carbon, therefore we will have to add up 3 additional bonds to it, and all will be the hydrogen bonds. Again, this carbon only single bond, so we will have to add 3 hydrogens in this one as well. This carbon is making 4 bonds already with other 4 carbons, so it will not take any extra hydrogen. 3 bonds for this one, and similar case basically, whichever, just to fill up the complete number of 4 carbon bonds, we will have to add up the hydrogens, and we get a structural formula, something like this at the end. Next is different types of structures usually seen in chemistry, and the molecule in all of these different diagrams is the methane or CH4. So A is representing the Lewis dot structure, which we discussed in the first midterm, as well as the B, which was tetrahedral shape. So the shape of the same methane will look something like this in the form of tetrahedral. C is again a tetrahedral carbon shown, but with dashes and with wedges. So these dashes and wedges are basically the bond. So these are the two dashes in blue, and then there are a couple of wedges shown as well with the other two hydrogens. Now this simply tells us that the dashes are representing the bonds which are in a same plane, whereas the wedges are showing that they exist in a different plane, so to make the three-dimensional structure. And the simplified version of this one is simply the drawing of the tetrahedral carbon atom, or known as the stick drawing basically. D is showing us the stick drawing, in which there are no wedges, basically simply the same four bonds with hydrogen. So it does not gives us the complete information about the 3D structure. And the last one, or E, is the ball and stick model, whereas the balls are representing the atoms and the sticks are representing the bonds that are present between them. Next is comparison of structure of two small alkanes, ethane and butane. So ethane has two carbons in it, C2H6 is the formula, whereas butane has four carbons in it, so C4H10 is the formula. So when a compound or an alkane has two carbons, it's usually represented by a straight line bond between them. Whereas when there are more than two bonds, the bonds will be shown in a zigzag-like structure, as we can see here. And the bond between two hydrogens is going to be 109.5 degrees, both between ethane and the butane structures. So the stick and wedge structure is shown in A and C, whereas the ball and stick in B and D of these ethane and the butane. Next up is a concept known as isomers. So many carbon compounds exist in the form of isomers, and this isomerism has got a lot of different types. The most simplest type you can say is the structural or constitutional isomers, and these are the compounds with same for molecular formula but different structural formula. So structural isomers are same molecular formula but different structures or different structural formula. So the example is butane and methyl propane, and we can see the structures are totally different. One is linear alkane, the other one is branched alkane, but both have the same formula, C4H10. So the number of atoms is exactly the same between these isomers.